Hello, everyone. Welcome back. This is Monica Lupion. I'm your instructor in CE 318 Heat and Mass Transfer in the summer session. Today, I'm going to cover one particular case or one dimension steady state conduction. It's the case of the fin or extended surfaces. And you can get more information in the chapter section 17.3. If you remember in the previous video, I went over the differential equations for heat transfer, particularly in the case of conduction. And we covered two particular situations when one is the concept of the critical thickness of insulation. And we apply that, let me put a pointer, we apply that to the case of a cylinder. And then we also discuss how to solve the differential equation of heat transfer when there is heat generation. Now, today, I would like to focus on the utilization of extended surfaces. This is a very common practice in industry when we want to maximize or promote the heat transfer that it has to be removed from a particular process. And I'll give you some examples about that. This is not new. We copy that idea from nature, and I'll give you some examples as well. So what we have to say about fins. As mentioned, this is not something that we humans created, but it was we copied from nature. There are different examples. One is, for example, the case of the polar bear, and they have air, which is white. The color is white also for camouflage, but in addition to that is to control the heat radiation and a way as well to control the temperature of the body. The hair, this would be hollow hair, and this is a fin. In other examples that we find in the nature, for example, this case of the fennec fox in North America, you have like long ears. It's not only to hear better, but also to control the temperature of the body. Same for an elephant, or if we take a look to the sea, there are different marine species that they use some sophisticated circulatory system with a lot of different fins that they can use to flow blood over those or through those fins to regulate the temperature of the body as well. So going from nature to industry or applying the same concept from nature to industry, we use the same idea. We increase the surface area as a way to promote the heat transfer from a system to the environment. An example of this is the computer. The computer generates a lot of heat because of the operation. We need to remove the heat from the system, otherwise we could damage the different components of our computer. One way to do that is to install something like this. I'm pretty sure that everybody have seen one of these. So we put a lot of extended surfaces to increase the surface area, and with that we can increase the heat that is removed due to convection. If we want to promote this even further, we can install a fan. I'm not sure if you hear the fan of my computer right now, but because I'm doing different things, for some reason, it gets heated and the fan is always on every time I record a video. So if you remember the difference between natural convection and forced convection, I mentioned that with forced convection, we use a mechanical device, for example, a fan, to promote the removal of heat. What we do is to increase H, the convective coefficient H. And if we increase H, we're also increasing Q. So this is another example of forced convection versus natural convection, okay? We can find fins with many different geometries. In this course, we're going to assume, just for simplification purposes, that we're going to have uniform cross sections, but in reality, you can find many different geometries. As long as in extended surfaces, this could be considered as a fin as well. If we have a pipe line, very common as well, we can find either circular fins, like this case, or straight fins when the fin is installed over the length of the pipe. Okay, we're gonna see. I mean, the approach that we're gonna take in both cases is the same. Just the surfaces, of course, they are different. So let's get a little bit closer to a fin, and let's imagine that we define a cultron volume, delta X is defined here in this drawing, and if we apply conservation of energy, we can say that the heat that is getting into this cultron volume is equal to the heat that is getting out due to conduction plus the heat that is being getting out due to convection. So in this equation here, this is the heat getting into the system due to conduction. This is the heat that is getting out of the system due to conduction, and this is the heat that is getting out of the system due to convection. If we apply the equations that we already know, the Fourier equation and the Newton's law of cooling for conduction and convection respectively, then we know that the heat due to conduction is equal to the thermal conductivity times the area dt dx. And the heat due to convection is equal to H times the area, in this case the extended surface area, times delta T. Okay? If we play around with this equation, if we divide by delta x and we evaluate delta x going to 0, which is similar to say that we're integrating this equation, we play around, and if we assume that the area of the fin is constant, we get to this equation here. It's a differential equation, okay? In order to solve this differential equation, we will have to do the integration, and also we will have to define two boundary conditions in order to define the two constants that will be resulting from the integration process. These, as you can imagine, depending on the geometry, could be a little bit tricky and challenging. I'll show you how to solve it. And there is a long development in your textbook, but usually we engineers are very practical and we take practical approaches. In this case, we are gonna use a concept that will help us solve this problem without going through the analytical solution and the integration. So we're gonna define fin efficiency. And the fin efficiency is the ratio of the actual heat transfer from the extended surface divided by the maximum possible heat transfer that can be released from the surface. So if the surface without the fin, if the surface is T0, the maximum heat that can be transferred between the surface and the environment is H area T0 minus T infinity. If we have some elements here, and this, instead of being a T0, this would be a temperature T, so the heat that will be released from the fin will be equal to H, the area of the fin, T minus T infinity. So if we applying the concept of fin efficiency, the fin efficiency will be the ratio of the actual heat, because each and area will cancel, okay, because it's the same in both cases. And this is the equation that will define the fin efficiency. Okay, usually this temperature here is very tricky to get to know. Therefore, we're gonna find a different way to calculate the fin efficiency without getting to know this temperature here, because as I mentioned, it's gonna be a little bit difficult to get. I'll show you in a minute why. So let's get back to the problem. This is the problem, this is the equation that we need to solve. And I mentioned that we can either try to solve it mathematically, analytically, and therefore we will need to solve the differential equation. We will have two constants here that we will have to define using boundary conditions. But even when considering a relatively easy geometry as a flat plate, as you can see here, the solution is not that easy. And so we're going to try to find a different approach. We're going to try to avoid the analytical solution, and we're going to try to use a more practical approach. As I mentioned, that's what normally engineers do. The practical approach that I wanted to discuss with you is to use the graphical method and to use the concept of this fin efficiency. We know already what's a fin efficiency. We know the definition. So how can we use this fin efficiency to simplify the solution of the differential equation or the solution of the heat transfer when there is a fin involved? Well, let's zoom out now and let's imagine that we have an element, for example, this can, and this will be the primary surface, and we install a straight fin, for example, this here, okay? And we need to calculate the heat that is being released in this element when we consider the fin. The total heat will be the sum of the heat that is going through or is going over this surface of the primary surface plus the heat that is being released due to this fin. Both of them, we need to take into consideration the contribution of both. So this is what it is explained here. The total heat is equal to the heat leaving the primary surface plus the heat that is leaving the fin. How can we define the heat due to convection that is leaving the primary surface? Well, I know that there is a primary surface defined as E0 times the convective coefficient H delta T, and delta T is defined as the temperature of the surface minus T infinity. Okay, we know that. Okay, let's go now to the fin. Okay, for the fin, we have the area of the fin, the convective heat transfer coefficient H. For simplification, we can assume that it's the same in both cases, delta T. But now delta T is not T0, is the temperature over the surface, for example, in this point. So we don't know the value of T, and I mentioned a few minutes ago that it's very tricky to get the value of this temperature. But then I remember that we defined this fin efficiency, right? And the fin efficiency, as you can see here, is the ratio between delta T over the fin and delta T over the surface. So we can say that T minus T infinity is equal to the fin efficiency times T0 minus T infinity. Okay, so we substitute that into this equation here, and so here we can say that this is equal to the fin efficiency times T0 minus T infinity. And that I know T0 is usually given in the problem. So I play around with this and I group different terms, and now I can say that the total heat is equal to H, which is known, the area of the primary surface, the area of the fin efficiency, which I don't know the value, and I will explain you in a minute, T0, which is also known, and T infinity, which is also known. So as soon as I get the value of the fin efficiency, I will be able to calculate the total heat considering an extended surface. How can I calculate this fin efficiency? There are different ways. In your textbook, there is an equation, and there is also this graphical method. I prefer the graphical method. I think it's quicker, and we don't need to be very, very accurate. So I think this should be fine. So in this graphical method, what we have is the representation of this parameter here, which is a function of the radius, the convective coefficient H, and the thermal conductivity K, and the thickness of the fin, and this is represented here as a function of the fin efficiency. So what we have to do is first to calculate this value here, and we normally have all the elements that we need. Second, we need to identify which line should I use, and the line is a function of the radius of the fin compared to the base element. Okay, so let's imagine that R L over R 0 is equal to 1.8, for example. Okay, this is just an example. So we go to the graph and we're gonna use this line here, which corresponds to 1.8. And let's imagine that the parameter 1 is 3.0. We get here and the intersection, we move to the left, and we get the value of the fin efficiency, for example, 0. In this particular example, 28. With this value, we get back to the equation here, and we will be able to calculate the total heat in a very easy way. Two things about this graph. One is that, well, if we have a straight fin, like the example that I mentioned, so not a circular fin, but a straight fin, okay, like this example, we have to consider, we have to pick this line here. So when the ratio between the radius is equal to 1, okay? This is number one, in case if we have a straight fin. Second thing that we need to pay attention to, the thickness. The thickness is defined here as 2t. Therefore, when we calculated this parameter here, we have to use t, which is half of the thickness, okay? Do not forget that. Okay, so these two things, okay? But other than that, you can see it's relatively easy to calculate the value of the fin efficiency. So in general, how can we solve a problem when there is fins incorporated? We are gonna try to use the analogy with the electrical circuit. Let's imagine that there is an element A, and like this one, and we incorporate fins. Okay, so the element A will be, for example, if there is some convection inside of the can, and then we have the element B, which will be the primary surface without the fins, and C will be the fins inside themselves. Okay, and B and C are two elements in parallel, each one having different thermal resistance. The resistance of the primary surface due to convection is going to be 1 over H over the primary surface, and the thermal resistance of the convection due to the fin will be the same, but we will have to incorporate the concept of the fin efficiency. And that's it. Then you solve this circuit, as we know. First the parallel and then in series, whatever element is downstream. And with that, you can easily calculate the value of the total heat. Okay? Okay, so in summary of this lecture here of the one-dimensional steady state conduction, this is the general equation of heat conduction. You need to know how to simplify that, considering the different cases. If we don't have heat generation, this term here is cancelled. If there is no dependence with time, this other term can be also cancelled. And then from there, we went over the different simplifications, and one of the cases, one dimension steady state conduction, is the Laplace equation. Okay, And also, a particular situation that we study is the critical thickness in pipes, the concept of the critical radius in a pipeline. And now I just went over the case of having fins to increase the surface to promote heat transfer and the use of this graph to calculate the fin efficiency in order to incorporate this fin efficiency into the general equation of the heat. Okay, I'll go over an example during the recitation class that you will have also available on UWeLearn. Go over this example with fins. I will also post a few examples for quiz 1 for you to practice, and at least one of these examples is related to fins. It's not easy, I mean, it's not complicated, sorry. You just need to know or pay attention to a few details, but you need to practice in advance if you want to solve it correctly. Okay, so revise the information, review the information, and if you have any question, please let me know. Thank you.